So, in the previous video, we introduced a non-commutative group structure on the space R3 with the purpose of preserving the distributions of planes that you see in my back. The group law was this one here. So R3, equipped with this group structure, is called the Heisenberg group. However, this is just a coordinate expression of the Heisenberg group. It is just one of the many models.
The Heisenberg group has also a matrix model. So it can be seen as a subgroup of the group of invertible 3x3 matrices. And in fact, it can be seen as the group of 3x3 matrices that are upper triangular, that are equipped with the usual matrix product.
So let's see what this means. So now we present the Heisenberg group as a matrix group. So let's consider set G of all those 3x3 matrices of the following form: A, C, 0, 1, B, 0, 0, 1. So this is a 3x3 matrix where A, B, and C are real numbers. There is 1 in the diagonal, 0 below the diagonal. Okay, so of course this is homeomorphic to R3, but this is a subset. So you will see it's a subgroup of the general linear group of 3x3 matrices with real coefficients. Okay. So the group structure is the structure of given by multiplication of matrices in GLN. So, namely, if you have two matrices, I find this useful because one doesn't need to remember the previous formula for the product of the Heisenberg group, but just need to remember how to multiply matrices, right? So, row by column, 1 third. Row by column gives you A prime plus A plus A prime, this one and this one. So this is C prime plus A B prime plus C. C prime plus A B prime plus C. And then you can continue the exercise. In short, this is the rest of the matrix. You see, it's very similar to the previous product law we considered in R3. See? It is the sum plus the third coordinate. There is a non-Abelian factor, right? So now you only have A B prime instead of also having minus A prime B. But we will see that this is the same. Okay, so this is a matrix group, and it's convenient also because now we can use the theory of matrix groups. For example, the exponential in this Lie group is just going to be the classical exponential of matrices, and the tangent of the identity, which is called the Lie algebra, is the following. So the Lie algebra of G, namely the tangent space at the identity matrix, is like this G, the matrix of this A, C, B, C. Now it's similar to the previous one, but now we have 0 in the diagonal. Okay, So now, a basis of this Lie algebra is given by the following vectors. Basis of G is x, is the vector 0, 1, 0, 0, 0, 0, 0, 0, 0. Y is 0, 0, 0, 0, 0, 1, 0, 0, 0. So see, there the one referring to the upper diagonal, and then there is z, is 1 in the upper corner. Okay. An exercise that I suggest you to do, which will teach you something from the following the course, is that if you do the commutator x, y minus yx, this is multiplication and difference of matrices, you exactly have the matrix.
You get z. It is equal to z.
Okay. As you said, now in this group, it's also easy to calculate the one parameter subgroups. One parameter subgroups are of the form. So let's say the curve associated to ABC times t, namely the exponential t times the arbitrary matrix is not remember. Yes, and this here 0, 0, 0. Okay, what is it? Okay, so how to do the exponential of matrix? The exponential of matrix is started with identity plus the matrix T 0, A, C, 0, 0, B, 0, 0, 0, plus now the square of the matrix. So it's the square 0, A, C, 0, 0, B, 0, 0, 0, square plus and so on. Okay, so this is okay. In general, you continue with the expansion of the exponential. But now we'll see what happens here. Okay, we have e plus t 0 and c 0, 0, b 0, 0, 0. Now let's do this square. Okay. Now you see, okay, going to be 0 in the diagonal, and then also in the upper diagonal, what's happening is that right row by column is again going to be 0. So what you're going to have is a matrix that is 0 in the diagonal, 0 in the upper diagonal, and then the next diagonal is right by column. It is exactly AB. AB. Now you see that if now I take again a product of this matrix with this matrix, then nothing will survive, right? Because whenever I take this column, then there is no row that makes it something different than 0. So we have plus 0. Okay, so in other words, here there was really nothing. So we can write now in a single form. This is going to be 1 AT CT plus ABT square over 2 0 1 BT 0 0 1. So these are the one parameter subgroups. Okay, now let's clarify that this group is the same of the previous group. So in other words, like this product law really gives a group that is that is isomorphic to the group that we saw in the previous one. Okay, now I'll just give you the map. You see, so claim the map phi x y z to 1 x z plus 1/2 x y 0 1 y 0 0 1. This is a Lie group isomorphism from the Lie group R3 equipped with product. Remember the product, so the product was x, y, z times x prime, y prime, z prime equal, so you have the sum plus 1/2 of x, y prime minus y x prime. Okay, so it's an isomorphism of this group. You consider the domain and in the target, the above, and the Lie group of 3 by 3 after triangular matrices with matrix product. Okay, so it's very easy to show that this is a change of variable, that it is continuous, that is invertible, and this is also a homomorphism. So the image of the product is the product of the image. Okay. Moreover, the differential at the identity of this map is really the identity, and since the vector fields that we were considering in the previous video to the vector fields x, y, z. Okay, actually, this is not a strange fact, because what we'll see later is that there is actually only one possibility for a non-commutative abelian group in non-commutative nilpotent group in dimension 3. Okay, so it's easy to show that this is a group law and that this is nilpotent. So since, in other words, since this is a nilpotent group simply connected and three-dimensional but not abelian, it must be the Heisenberg. This is what we will see in the next part.
The Heisenberg group admits also a characterization that is completely algebraic. Indeed, now we are going to see that in 3 dimensions, there are only 2 possibilities for a 3-dimensional simply connected nilpotent Lie group. One is, of course, the abelian Lie group, and the other one is indeed the Heisenberg group. Let's see how to prove this simple fact. Let's see what are the properties of the Heisenberg Lie algebra. So the Lie algebra of the Heisenberg group has the property that it is spanned by 3 vectors, right? 3 vectors. We call it x, y, z, whose only
only non-trivial relation is x bracket y equal to z. Okay, and the other brackets like x with z or y with z are equal to 0. Okay, this is the only non-trivial. Okay, let's discuss a little bit more about this for the first model we had, right? Remember, so for example, in the model in which x is dx minus y over 2 dz and y is equal dy plus x over 2 dz. Then what is the bracket? Okay, let's recall how to do the bracket of vector fields. Okay, so this is x applied to y minus y applied to x as differential operators. So what does it mean do x applied to y? So we look at y, and now we differentiate the coefficients using the vector x as a derivation. So this is y. Let's do it one piece at a time. So I look at this vector, okay, and now I look at the coefficient. Okay, this is constant. So if I differentiate with respect to x or respect to y or z, is going to be 0. Second part is more interesting. Okay, if I now differentiate this with respect to x, now if I differentiate with respect to x, then the differentiation will make this vector, this function become 1/2. So I'm going to have 1/2 dz. So it's going to be 1/2 dz. And this one nothing, because again, there's nothing depending on z. Vice versa, now we have to differentiate x with respect to y. And the only thing that is surviving is when I look at this component here, and I differentiate with respect to y, and I'm going to have minus 1/2 times dx. But I also had another minus here, okay? So it's called plus 1/2 dz. And this is dz, which is what we define to be the vector z. Now it's also very easy to check that, you see, these vectors don't depend on z, and this vector here do not depend on x, z, or y, or z. So the bracket of x and z, and also y and z, is equal to 0. Okay, so our model had this property here. In particular, also, you see, this tells you that if you take the bracket of 3 vectors, see, then okay, if you the first two and you perform the bracket, okay, if the first two were x and z, x and y, you get z, but then z will give 0 bracketing with anything else, right? So let's write this. So in particular, the Lie algebra, the Heisenberg algebra, the Heisenberg, the algebra has the property that any bracket, that the bracket of any 3 vectors, x1, x2, x3 of this Lie algebra has the property is 0. So x1, x2, x3 bracket is equal to 0 for all x1, x2, x3 element of the Heisenberg Lie algebra. So this will be summarized saying that the Heisenberg algebra, the Heisenberg algebra, the algebra has is nilpotent. I will explain. Is nilpotent. Nilpotent with nilpotency step, or just step 2. Okay, let's recall this terminology. So recall the algebra G is nilpotent with step S if the Lie bracket of every S plus 1 of its vectors is 0. So it's the iterated bracket. X1, X2, XS plus 1 equal to 0. We're now ready for proving our claim. So the claim is that there are only 2 3-dimensional simply connected Lie groups, nilpotent Lie groups namely the Euclidean, or what I call Abelian, the Abelian tree space, and the Heisenberg group. Okay, so the fact is, I mean, this theorem is actually, this exercise is about Lie algebras, because it's a general fact that a simply connected Lie group is totally determined by its Lie algebra. Okay, so let's discuss Lie algebras first. So indeed, consider G, the Lie algebra of one such group. So the fact is that the group G, let's call it G, the name of the group. G is nilpotent if and only if G is nilpotent. Let's observe that here nilpotent means 2 different things, right? So for Lie algebra means that the iterated Lie bracket are 0, Lie brackets of length S plus 1 are 0. Instead, for a group, nilpotent means that if you take the commutator, the iterated commutator, where the commutator of 2 elements A, B, now for group element is defined by A, B, A minus 1, B minus 1, right? So if we iterate, so in other words, if you take S plus 1 element and we do the iterated commutators, this is 0, okay? But this is a fact. Okay, so now we have a nilpotent and 3D, and it's still 3-dimensional, the algebra. Okay, so on observation, there exists Z non-zero in the center of G, because G is nilpotent y, right? So if S is nilpotent of step S, then, but not of step S minus 1, then it means that there exists a non-zero vector that then when you iterate with anything else, since this, you take a vector that is the bracket of S minus 1 vectors, of S vectors, has the property that whenever you iterate, you bracket with anything else has to be 0, and therefore is in the center. Take Z a non-zero bracket, a non-zero bracket of S elements, but this S is nilpotency step. Okay, now we have Z. Now just complete Z to a basis of G. So we have X, Y, and Z. So this is a basis of G. Okay, now remember that X and Y already commute with Z. Now let's see what do they do. Okay, so case 1, X and Y is equal to 0. But then all the brackets on the basis are 0. Then we are having an abelian algebra. Then G is commutative. Case 2, the bracket is non-zero. And then 0. And let's define it to be, let's call it W. Okay. And W is an element of the algebra. And therefore can be expressed in terms of the basis, ax plus by plus cz. Okay, very good. So let's see what are these coefficients. Let's look at the bracket between x and say w. Now, okay, sorry, x and, no, w and y. So we have ax plus by plus cz y. Okay, now z is in the center, so it commutes with y. Y commutes with y. So this is the same of writing a x y, namely aw. So now we have that when you bracket w with y, you again have a multiple of w. If these elements were not 0, then you see that this would contradict the nilpotency assumption, because it means that you can take w and multiply as many times with y as you want, and you will never get 0. So it cannot be nilpotent, right? So nilpotency implies that a is equal to 0. Similarly, bracketing now with x, we're going to have b or minus, we're going to have minus b. But again, b has to be 0. It has to be 0, right? So now, and therefore, c is different than 0, because we said that w is a non-zero element, right? So if this is not here, c cannot be 0. So now, up to replacing z with cz, still is in the center, we have that the Lie algebra, the relations of the Lie algebra, in the second case, are x, y equal 0, x, z equal y, z equal to 0. As I said before, the proof is concluded because we recall a fact: there exists a unique, simply connected Lie algebra with a given, for every given Lie group with a given Lie algebra. And we will go back to this fact and explain why, okay? But in other words, that's because the exponential map, in the case of the nilpotent group, really gives a covering, okay? Okay, good. So in case you have questions, I hope you know how to contact me to ask me questions and we can discuss.
If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel clicking below. Bye.